We now consider realistic case where the transmission line is actually terminated. Okay. So, let us consider the case where the transmission line is terminated, which is what would happen in a realistic scenario, right. So, you have a transmission line which would run for a certain distance, and then it might terminate itself into a waveguide, or it could terminate itself into a free space in rare cases, or it could terminate into a different load or a second transmission line or an antenna. It could terminate into anything onto this side, but then let us characterize whatever that termination by its terminal characteristic in the form of an impedance ZL. So, through this load ZL there will be a current IL flowing, and across this ZL will be the voltage VL. Okay. So, here you will have the source side of the transmission line. We have a transmission line of length L. Okay. This is the length of the transmission line, and what you have to observe here is that on the transmission line, okay, initially when you are looking at, there would be incident wave, right. So, it would be V0 plus e power minus gamma z, and you come all the way up to this point. Now, in dealing with these kind of situations, the convention is to actually take this as z equal to 0. That is, one assumes that you are actually sitting on the load, okay, and takes that as the point of reference or plane of reference as z equal to 0. This is kind of an older convention, but that is very popularly followed. So, we are going to follow that one. So, you locate your load at z equal to 0, okay, and then the input end of the transmission line will be located at z equal to minus L. This is how the z axis is going. Now, initially if you assume that there is only incident wave, incident voltage wave propagating. So, this voltage wave would propagate, and what would be the value at z equal to 0? It would just be equal to V0 plus. But immediately you are stuck by something. On the transmission line the voltage seems to be V0 plus amplitude, but to the just immediately next to that one there will be a voltage of VL, right, and because you have connected, KVL dictates that V0 plus must be equal to VL. Clearly this should also indicate that I0 plus is equal to IL, and if you take the ratio of V0 plus to I0 plus, which is basically giving you the characteristic impedance of the transmission line, this would be Z0. This should be equal to VL by IL, which is equal to ZL. Now, it is possible that one chooses ZL equal to Z0. Okay, indeed most of the RF designers spend their time in trying to make ZL equal to Z0, but this is not always guaranteed, right. So, this is not always true that the load impedance will always be equal to the characteristic impedance. If that happens, then there is only incident wave, and this incident wave is completely absorbed by the load. But this does not happen in general, does not happen, or it is not true in general. So, this V0 plus by I0 plus is equal to Z0 should not be equal to ZL, which further implies that I0 plus is not equal to IL and V0 plus is not equal to VL. So, where have we gone wrong? Is KVL, KCL wrong? Well, KVL and KCL are not wrong. What is wrong is that you cannot satisfy this boundary condition just with an incident voltage wave. Okay, because of this scenario of termination with a different load than the characteristic impedance, there will be a reflected voltage wave with an amplitude of say V0 minus and propagating along minus z direction. So, it would be V0 minus e to the power gamma z. Therefore, the total voltage on the line, on the transmission line, okay, is the sum of forward going plus the backward travelling reflected voltage. This is something that we have seen, right. Now, for when we assume that you had only V0 plus e power minus gamma z, we found out the relationship between dV by dz, or we found out the relationship between I of z and V of z, and that ratio was actually Z0, right. Now, when you have V0 minus, if you assume for a minute that there is only backward propagating wave and then differentiate this one with respect to z, what you see is that gamma V0 minus e power gamma z should be equal to minus R plus j omega L into the current. Current will be I0 minus e power gamma z, and then when you look at the ratio of V0 minus to I0 minus, you will see that this would be equal to minus R plus j omega L by gamma. Again, writing gamma as square root of R plus j omega L into G plus j omega C, you will see that this is nothing but minus Z0. This is very crucial. Okay. So, the ratio of backward going or reflected voltage to the reflected current is actually equal to minus Z0. Therefore, if I know what is the voltage on the transmission line, I can write the current on the transmission line as V0 plus by I0 plus is nothing but V0 plus by Z0 propagating in the same direction. Therefore, I can write this as V0 plus by Z0 e power minus gamma Z, but the ratio of V0 minus to I0 minus is actually minus Z0. Therefore, this is minus V0 minus by Z0 e power gamma Z. Okay. These are the voltage and currents on the transmission line. Both voltage and currents actually consist of incident as well as reflected waves in order to satisfy the boundary condition. Have we actually satisfied the boundary condition? Well, let us look at what happens. Okay. Let us assume that V at Z equal to 0, which is the load that you are considering, right, must be equal to ZL clearly, right. So, at the load side, the ratio of voltage to current must be equal to ZL, and this should be equal to V0 plus V0 minus divided by V0 plus, this Z0 goes on to the numerator, minus V0 minus. Okay. It is customary to factor V0 plus out. So, you get Z0 into 1 plus V0 minus by V0 plus divided by 1 minus V0 minus by V0 plus. Now, what is V0 minus? This is the incident V0 plus amplitude, and this is the reflected amplitude at the load. Okay. So, at the load, your V0 minus by V0 plus is the ratio of reflected to incident voltage, and this ratio is denoted by gamma L. This is the reflection coefficient as measured on the load L. Okay, on the load, and that load is characterized by gamma L. So, what you have is ZL given by Z0 into 1 plus gamma L by 1 minus gamma L. You can actually use this equation, turn it around to find out what gamma L is. Gamma L is given by ZL minus Z0 by ZL plus Z0. This equation is very important. So, let me box this equation out. Okay. This equation actually is giving you the reflection coefficient on the load in terms of the load ZL and the characteristic impedance Z0. Clearly, as you change ZL or Z0, the value of gamma L will also change. Alright. Now, we might also be interested in something that happens over here. Okay. So, let us say this is the load that we have connected, and this is the transmission line of length L that I have. So, Z equal to minus L corresponds to the input terminals of the transmission line, right. So, at the input terminals of the transmission line, what is the impedance Z in? This impedance Z in seen looking into the input terminals of the transmission line should clearly be the voltage at the source side or at the input terminals to the ratio of voltage to current, right. So, current at the input terminals. Now, using the expressions for voltage on the transmission line and current on the transmission line, substitute Z equal to minus L. What you get is V0 plus e power minus gamma L plus V0 minus, sorry, this becomes plus gamma L because you are substituting Z equal to minus L, and then you have V0 minus e power minus gamma L divided by V0 plus, there is a Z0 here, e power gamma L minus V0 minus e power minus gamma L. Okay. Factor this entire V0 plus e power plus gamma L out. So, what you get here is Z0 into 1 plus V0 minus e power minus 2 gamma L divided by V0 plus divided by 1 minus V0 minus by V0 plus e power minus 2 gamma L. But I already know what is V0 minus by V0 plus, that is precisely equal to gamma L. Therefore, the input impedance Z in is equal to Z0 into 1 plus gamma L e power minus 2 gamma L divided by 1 minus gamma L e power minus 2 gamma L. Okay. Now, you re-multiply this one by e power gamma L on both sides, okay, and substitute for gamma L as ZL minus Z0 plus ZL by Z0 and simplify the equation. This is not very difficult, this is just little tedious, but you can do it in couple of lines. So, when you simplify this, what you get is the input impedance to be equal to Z0 into ZL plus Z0 tan hyperbolic gamma L divided by Z0 plus ZL tan hyperbolic gamma L, where tan hyperbolic gamma L is actually given by e power plus gamma L minus e power minus gamma L divided by e power plus gamma L plus e power minus gamma L. This is actually the ratio of hyperbolic sin gamma L to hyperbolic cos gamma L. Okay. So, this is the input impedance, and you will be little surprised to see that input impedance depends on two things, right. It of course depends on Z0 if you leave that out. It also depends on the load impedance ZL. So, if I connect different loads, then that load would look very different at the input terminals of the transmission line. Okay. And it would also depend on what is the length of the transmission line that connects the load to the input. In fact, this observation that the length of the transmission line and ZL can influence what the input impedance of the transmission line is extensively used in analysis of RF and microwave circuits. Okay. So, it is in fact used to transform the impedance ZL by choosing an appropriate value of L and appropriate value of Z0 to whatever value of Zin that you want, so as to maximize the power transfer. Okay. We have a simplified expression for Zin for the lossless case. For the lossless case, what happens is that tan hyperbolic gamma L actually becomes J tan beta L. Why? Because gamma is equal to J beta for a lossless case, there is no attenuation. So, substituting this into the expression for input impedance will give you Zin as Z0 and ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L. Okay. So, this is the expression for input impedance. Now, let us look at some of the cases. First of all, if ZL is equal to Z0, what happens to input impedance? You substitute ZL is equal to Z0 here, so it becomes Z0 plus JZ0 tan beta L, Z0 plus JZ0 tan beta L. So, clearly Zin will be equal to Z0, right. If ZL is equal to Z0, then input impedance will exactly be equal to the characteristic impedance. It is completely independent of load impedance, and it is completely independent of the length of the transmission line. Okay. Suppose ZL is equal to 0, that is you short circuit the load side. With ZL equal to 0, the input impedance becomes JZ0 tan beta L, right. So, this is the input impedance. When ZL is open circuited, then Zin will be equal to, so with ZL being open circuited, this term becomes larger, this term becomes larger, ZL cancels. What you have is minus J cot beta L. Okay. Further, when beta L goes to 0, right, that is when the length of a transmission line is made very small, then this tan of beta L goes to almost 0, therefore, this will go away, and what you have is Zin equal to ZL. There is probably not much of a surprise in this expression. Okay. But what might be surprising to you is when you take beta L to be pi by 2. Okay. So, when beta L becomes pi by 2, tan of pi by 2 becomes very large. So, in this case this will survive, the JZ0 tan beta L in the numerator, and in the denominator JZL tan beta L will survive, and input impedance becomes J tan beta L will all go away, that becomes Z0 square by ZL. Okay. So, this is what would happen. On the other hand, when tan beta L goes to 0, that is when beta L goes to pi, tan beta L goes to 0, then Zin again goes to ZL. Oh yeah, we have already considered that particular case. When beta L goes to 0, tan beta L goes to 0, or when beta L goes to pi, again it would essentially be the same situation. Okay. So, these are some of the cases. Let us actually look at these two cases which seem to be very interesting. Okay. First, consider ZL equal to 0, which is placing a short circuit on the load and input impedance for a L length transmission line. So, this is the situation that we are considering. Okay, this is ZL equal to 0, and this is a piece of length L of the transmission line, and this is your input impedance seen looking into this. Okay, and this input impedance seem to be purely real. This is all as good as, or as this thing as having an inductor or a capacitor as an equivalent transformed load, right. If you actually graph how Zin changes as a function of L or as a function of beta L. So you can see that at beta L is equal to 0, this Z in will be equal to 0, and then at beta L is equal to pi by 2, between this 0 and pi by 2 the value of Z in keeps on increasing and it looks something like this. So this fellow is JZ0 tan beta L, and the equivalent impedance or equivalent reactance in this case would be that of a inductor. So the input impedance would look more like an inductor, okay, it would look exactly like an inductor for this particular case. At pi by 2, however, beyond this up to pi, right, you have this kind of a behavior. So in this region your input impedance looks like a capacitor, so the load looks like a capacitor. Here again the load looks like a inductor. Okay. A similar thing would happen when you consider Z in for ZL equal to infinity, that is for open circuit. In this case they would actually change slightly. Okay. It would start from capacitor, go through and then become an inductor. Okay. So here it starts off being a capacitor and then becomes an inductor at say pi by 2. Okay. So this is for the case of open circuited input impedance. In fact, by choosing whatever the value of L, you can choose whatever the required inductance or capacitance. In fact, you can generate a required amount of inductance and capacitance by choosing this L appropriately, okay, for a short circuited or open circuited load. Alright. We now come to very interesting scenario, okay, of standing waves. Okay. What we mean by this standing waves? Let us first look at what is the voltage phasor on the transmission line. Voltage phasor on the transmission line is, for a lossless line, we have V0 plus e power minus j beta z plus V0 minus e power j beta z. But clearly this V0 minus is related to V0 plus. You can actually take out this factor V0 plus e power minus j beta z if you want. What you get is e power minus j beta z plus gamma L, because this V0 minus is gamma L, and gamma L itself could be complex because gamma L is ZL minus Z0 by ZL plus Z0. It could be complex, so it can be written in terms of its magnitude and a certain angle, right. So you have e power j beta z plus phi L, where phi L is the phase angle. So what we have written is reflection coefficient gamma L as magnitude of gamma L times e power j phi L. Okay. So this is what you would actually see, okay, on the transmission line. This is the voltage phasor. Okay. Let us consider some cases when ZL is equal to n z naught, where n is a integer. Okay. So in this case what would happen to gamma L? Gamma L will be n z naught minus z naught by n z naught plus z naught. This is nothing but n minus 1 by n plus 1. This would actually be a completely real quantity for n being an integer. Suppose n is equal to 0. In this case gamma L is actually equal to 0, and then the voltage phasor V of z will simply be equal to V0 plus e power minus j beta z, right. This implication that gamma L equal to 0 or no reflection is simply telling you that ZL equal to Z0 and the entire incident voltage is absorbed by load. Okay. Entire thing is absorbed by load. Okay. Consider a second case which is very interesting. You short circuit the load side. Okay. So if you short circuit the load side, your gamma L will be equal to minus 1 because ZL is equal to 0. So you get gamma L of minus 1. You can, if you want, find out what is the magnitude of gamma L, which will be equal to 1, and the phase angle phi L will be equal to pi. Now substitute these expressions into the voltage phasor expression on the transmission line. So what you see is V of z is equal to V0 plus e power minus j beta z minus e power plus j beta z. But this is nothing but minus 2j V0 plus sin beta z. So the phasor that you see is actually minus 2j V0 plus sin beta z, and if you now try to find out what is actually V of z and time, that is in terms of both space and time, you see that this is real part of minus 2j V0 plus sin beta z e power minus j, sorry, e power j omega t. right. The real part of this, assuming that V0 plus is real, is nothing but you split this e power j omega t into cos omega t plus j sin omega t, but cos will not give you the real part. That j sin omega t, j and minus j will cancel with each other. What you get is 2 sin beta z sin omega t. This is certainly not in the form of some function t minus z by v. So, this is not in the form of a propagating or a travelling wave. This is an example of a standing wave, okay. Because you go back to this one, in the case of n equal to 0 and gamma l equal to 0 situation, your v of zt will be equal to some v0 plus cos omega t minus beta z. This is an example of a travelling wave, whereas the case where you have just seen the ZL equal to 0 short circuit is an example of a standing wave, okay. If you plot the voltage phasor, magnitude of the voltage phasor for this particular case, at z equal to 0 is where the load is, and at that load point sin beta z will be equal to 0, and thereafter it will go as magnitude of sin beta z, right, with a maximum amplitude of 2 V0 plus, okay, as you can see from this expression. You have to observe that there is a minimum at the load, okay, then there is one more minimum at a different location on the transmission line, right. This is also a minimum. There is actually a maximum in between two minima, that is obvious, right. So, if you go from minima to minima, there has to be one maximum. But where are these minima located? Well, the first minima is located at z equal to 0, and subsequent minima must be located whenever this sin beta z goes to 0. When does sin beta z go to 0? Beta z goes to 0 when the sin beta z goes to 0 when beta z is actually n pi, because at n equal to 0, that is at load z equal to 0, you have a minima. At pi, right, when n is equal to 1, again you have a minima. The minus sign simply indicates that the load is counted at z equal to 0, and all the further things are counted backwards. You know, the transmission line extends from z equal to 0 to z equal to minus L. You can find out this relation, you can better put this relationship in a slightly different way. This beta can be written in terms of wavelength as 2 pi by lambda, okay, times z will be equal to minus n pi, okay. And you can actually see where the minima are located. Minima are located at minus n lambda by 2. So, n equal to 0 being the fundamental position where the minima is. Thereafter, at every lambda by 2 there is a minima. Where will be the maxima? Well, maxima for this one would occur whenever beta z is equal to pi by 2, right. It cannot be n pi by 2, it has to be 2n plus 1 pi by 2, and this has to be a minus, and these are the locations for maxima. In fact, the distance between maxima to minima magnitude must be equal to lambda by 4, okay. So, if this is at z equal to 0, or in terms of lambda this is 0, and the next minima occurs at a lambda of lambda by 2, the maximum must occur at lambda by 4. A very similar relationship you can find for ZL tending to infinity, that is for the open circuit. Here though the voltage phasor becomes 2 V0 plus cos beta z. This is still a standing wave, okay. This is still not a wave which is propagating, but if you were to plot this V of z on the as a function of z, you will actually see that initially there is a maxima, then there is a minima, then there is a maxima and a minima, and then it goes like this, okay. Then it goes like this for this particular case when there is an open circuit. So, you can see that there is initially a maxima where the minima for this one is located, and minima is located for the open circuit where the maxima for the short circuit is located. Again, you can find out when this would be minima and maxima. Locations of minima will be when beta z is equal to n pi, or rather minus n pi, because at n equal to 0 cos of 0 is maximum, at n equal to 1 and at pi cos of pi is minus 1, but the magnitude is 1, therefore that is actually, sorry, this is actually maxima, right, because these are maxima. So, maxima are located at beta z equal to minus n pi. Minima on the other hand are located whenever this cos beta z goes to 0, which means there has to be pi by 2, 3 pi by 2 and so on. So, this would be minus 2n plus 1 pi by 2. again the difference between or the distance between maxima and minima will be equal to lambda by 4. Okay. So, these are the standing waves that you would see on a transmission line. Now, let me actually just give you something to think about. Okay. What would happen when gamma L magnitude is less than 1? Okay. So, just think about this. The answer is simple, but I do hope that you first think about this very clearly and then convince yourself that in the case of gamma L being less than 1, this is how the voltage phasor magnitude looks like. It will not reach the maximum of 2, it will not reach the minimum of 0, but it would be located somewhere in between. Okay. And this is what would happen for gamma L less than 1, and sometimes we are actually interested in finding out what is the ratio of this maximum magnitude to minimum magnitude. Okay. This ratio is called as standing wave ratio. Okay. Standing wave ratio gives you the ratio of maximum voltage phasor to minimum voltage phasor. Okay. When will the voltage phasor be maximum? Whenever, if you go back to the expression for the line. Okay. So, you can see that this is the expression. In this case, maximum will occur whenever you have this beta z plus phi L being equal to 0. Okay. So, you can take this out. So, then this would be e power j 2 beta z phi L. So, when you factor this out, what you get is 1 plus mod gamma L into something. When that phase factor is equal to 1, you get a maximum value. Okay. And that maximum value is given by 1 plus mod gamma L. Similarly, the minimum value is given by 1 minus mod gamma L. Okay. And therefore, the ratio of these two, which is the voltage standing wave ratio, is given by 1 plus mod gamma L by 1 minus mod gamma L. This is denoted by the symbol S. Okay. And is given by 1 plus mod gamma L by 1 minus mod gamma L. In terms of S, one can invert this relationship and say gamma L is equal to S minus 1 by S plus 1.